Hey guys, so in this video let's talk a little bit about units. Right, these are the invertible elements of a ring. So let R be a ring. This should be the last of the videos which you can consider like the class from Friday, April 2nd. Okay. So suppose A is in the ring, A is non-zero, and there exists B such that AB equals 1. Okay, then A is called a unit. Okay, this is our definition. Oh boy. Okay, we're back. Right, and the set of all the units, we'll call that R cross. Set of all units it's denoted by R cross is just all the elements of R such that A is non-zero and there exists B with AB equals 1. Okay. And then our proposition, we can prove a quick proposition that says R cross is a group under multiplication. Okay. Well, I don't want to belabor this proof too much, so let's just try. We have to show that it's closed under multiplication. So for xy in R cross, xy is also in R cross since, you know, xy times x inverse y inverse is just well, what should we do? I guess we should do xy times y inverse x inverse. That'll be quicker. Then y times y inverse will be 1, and x times x inverse will be 1, 2. Okay, so that tells us that xy also has an inverse if y and x do. And of course, if x and y are both non-zero, oh yeah, so why isn't it possible for xy to be 0? If xy equals 0, then you know, x y inverse equals 0 y inverse, that's 0. And but y inverse is x times 1, which is x1, which is just x times 1, which is x. So x equals 0, which means that x is not a unit. Okay. Okay, that's just kind of like some technical thing. So if I take any two units, I multiply them and I get a unit. That's good. There's also an identity under multiplication. Well, it's just the identity of the ring, right? 1 is in R cross since oh yeah, what do I need to assume? only if R is not the zero ring. Okay, and this is where I use that hypothesis, which is why I had to go back and add it. Sorry about that. But 1 is a unit since 1 is not equal to 0. This is that part. And 1 times 1 equals 1. In other words, 1 has an inverse, right? Okay, so this R cross, this is closed under multiplication. It's non-empty. Or sorry, but this is showing that so now we have a multiplicative identity. So if x is in R cross, then x times 1 equals 1 times x equals x. Okay, and then the other properties of the group laws all follow from just the axioms of a ring. Like for example, and actually you get an abelian group. So this is we can just add in, get an abelian group because we have a commutative ring. Okay, so other axioms go here, but we won't do that. Okay. So whenever I have a ring, I look at all the invertible elements and I get a group. Okay, let's do a couple examples of that. So what we can ask, what are the invertible elements in Z? These are the integers such that the integers a such that there exists another integer b with a times b equals 1. And actually there's only two. There's 1, of course, is one of them, and -1 is the other, right? Okay, on the other hand, like let's start with the units of R. Well, this is the set of all real numbers that are non-zero. Because in a field, all the non-zero elements are invertible. Okay. We could also look at the invertible elements of Z mod 30. Okay, we've actually already seen this. These are the congruence classes, which correspond to integers which are coprime with 30. So we have 1 bar, 7, 11, 13, 17, 19, 23, 29. Yep. And this is going back to the Euler 5 function 530. Well, if you remember, this is phi of 2 times 3 times 5, phi of 2 times phi of 3 times phi of 5. Well, that's 2 minus 1, which is 1, 3 minus 1, which is 2, 5 minus 1, which is 4, which is 8, right? So this group of invertible elements has 8 elements, and phi of 30 is also 8. That is how it works. Okay. Can also look at the invertible elements in the ring of polynomials. These turn out to just be the units of the field. Okay, so those are a few examples of units. Okay, so that is enough for this video. I also want to talk about divisibility, which we already saw in terms of principal ideals. But I want to talk a little bit about divisibility and irreducibility. Okay, so